Hello, everybody. Today we will be solving problem 1 of the 2020 USAMO. The problem reads, let triangle ABC be a fixed acute triangle inscribed in a circle omega with center O. A variable point X is chosen on minor arc AB of omega, and segments CX and AB meet at D. Denote by O1 and O2 the circumcenters of the triangles, triangle ADX and BDX respectively. Determine all points X for which the area of triangle O1, O2 is minimized. Okay, so the first thing we should do on every Olympiad problem is draw a large, accurate scale diagram, which I have gone ahead and done. And, okay, we want to minimize the area of this triangle O1, O2. So I'm going to make a few claims. The first claim is that triangle O102 is similar to triangle CB8 in that order. Let's go ahead and write that down. Okay, but before we go and prove that, I'm going to add a few points to this diagram. First of all, I'm going to make the intersection of point O102 with XD be point T, and this one over here is point D. I'm going to make this BT, and it turns out that since O1 and O2 are both on the perpendicular bisector of XD, because remember triangle AXD, the perpendicular bisectors intersect at O1, and triangle BXD has perpendicular bisectors which intersect at O2. So the perpendicular bisector of XD goes through both O1 and O2, so O1, O2 is the perpendicular bisector, right? And that essentially means that T is the midpoint of XD and that this angle O1TD is right. Now I am going to extend O01 to meet AX at a point R. And for the purposes of this problem, we assume without loss generality that angle XDA is acute and or right. So less than or equal to 90 degrees, and thus O1 is inside triangle AXD, and similarly O2 is outside of triangle BXD. So R is the midpoint of XA, and this line is perpendicular for the same reasons as before. R is on the perpendicular bisector. O1 is on the perpendicular bisector of AX, as is O, and similarly O02 is perpendicular to XR at the XB at the midpoint, which we will call S. Okay, now I'm going to claim that triangle O01, O2 is similar to triangle CBA. And the way I'm going to do that is I am going to first look at this angle over here, this orange angle, O2, O01, which we'll notice is equal to angle SOR. And then we'll notice that since angle XRO is 90 degrees and angle XSO is 90 degrees, and they sum up to 180 degrees, this quadrilateral XROS is cyclic. And what does that mean? It means that angle ROS equals 180 degrees minus angle RXS, and angle RXS is angle AXB. So, and since ACBX is cyclic, angle AXB, so this is 180 minus angle AXB. But since ACBX is cyclic, 180 minus AXB is the opposite angle ACB. So this is equal to angle ACB. Okay, now we take a look at, okay, so first let me mark this angle in orange. And I'm going to take a look at this angle, O0102, which I will mark in yellow. And in particular, then I'm going to look at this quadrilateral, XRO1T, this one, right? which means that angle O2, O10 is equal to 180 minus angle T01R. But since angle XR01 and XT01 are both 90 degrees, they add up to 180 degrees, which means that XR01T is cyclic. So 180 minus this angle over here is this angle RXT, which is also angle AXC. So let me equals angle AXC, right? But since quadrilateral ACBX is cyclic again, and angle AXC subtends arc AC and angle ABC subtends arc AC as well, angle ABC is equal to angle AXC. Okay, so that those two angles are equal as well. So angle O0102 is equal to angle ABC. Right, and since the two yellow angles here and there are equal to each other, and the two orange angles here and there, they're equal to each other, we have by angle-angle similarity, this is true. Right? Triangle O0102 is similar to triangle CBA. Okay, and since, let's stop for a moment and look at what we want. We want to minimize the area of O0102. I will relabel this in green. We want to minimize this area, right? And how do we minimize this area? We just, well, since triangle ABC is fixed, so the area of ABC is fixed. So I can write it as the area of ABC is fixed. And we know that the area of O0102 needs to be as small as possible. So O0102 over ABC, their areas. This must also be as small as possible because area of ABC is fixed. But since triangle O0102 and triangle CBA are similar, we can write this as the similarity ratio squared. And since the ratio is O102 over BA, so AB, it's this quantity squared. So we just need to minimize this thing. Okay. So I will write this for safekeeping. We want to minimize O01 over AB. And I'm going to go a step farther and make my next claim, which is that triangle XO102 is similar to triangle XAB. And this is not hard to prove. And so what I'm going to do is I'm going to first use a different color. I am going to draw XO1 and O1D. Okay. And then I'm going to label this angle XO1O2 in blue, right? But since O1T is the perpendicular bisector of XD, means that angle TO1D is equal to XO1T. So we can write angle XO102 equals to angle XO1T because O1T and O2 are collinear. This is equal to TO1D. Right? So 2 times angle XO1O2 is equal to angle XO1D. And angle XO1O2 is equal to half of angle XO1D, but we notice that XO1D, this angle over here, it subtends arc XD of this circle, right? Which means that half of the angle is going to be this angle over here, because XAD is an inscribed angle, which is half the arc, right? So half of angle XO1D is equal to angle XAD. Okay? Which is equal to angle XAB. So we've got one equal angle, XO102 and XAB. Now we do the same thing for the other angle. So I will do this one in pink. So angle XO201 is, well, we can draw O2D, right? We draw O2D and O2X. So angle XO201, which is XO2T, is equal to this angle. And this angle is twice of this angle, since arc XD of this circle is subtended by this inscribed angle and this angle in the center. So this pink angle, angle XBA, is equal to angle XO201. And since these two pink angles are equal and these two blue angles are equal, we have AA similarity gives this similarity is true as well, right? So now we can realize that the similarity ratio of these two triangles are also O1, O2 over AB, right? But because of this over that, but we can also write it as XO1 over XA. And, right, so XO1 over XA is the ratio we wish to minimize. But if we take a look at triangle XAD, we have XO1 is circumradius. XO1 is the circumradius. And we know that by extended law of sines, 2r equals AX over the opposite sine of the opposite angle, sine of X dA, right? So R over AX equals 1 over 2 sine angle X dA, right? But R is XO1. So we want to minimize this thing, 1 over 2 sine of angle X dA, right? And minimizing this thing is equivalent to maximizing that. So we want 2 sine of angle X dA to be as large as possible. So we want, and since the maximum of sine is 1, we need 2 sine of X dA to be equal to 1. That happens when angle X dA is 90 degrees. So the area of triangle O0102 is minimized when this angle is the right angle. Therefore, X is such that X is on circle omega and CX is perpendicular to AB. That is the point on the circumcircle with O0102 having maximum area. Thanks for watching, and I will see you next time.